Hello, my name is Kaito. I am a 10th grader at the International School of Kenya. For my STEM Pathways project, I decided to construct a Michelson-Morley interferometer to identify the key components of a gravitational wave detector, as well as understanding the fringe patterns of the superposition of light. The existence and the detection of the waves is strong evidence that Einstein's general theory of relativity is correct. Moreover, they allow scientists to take a closer look at astonishing events of black holes and neutron stars merging. The criteria is to replicate the Michelson-Morley experiment to understand the superposition of waves. However, creating this interferometer has some constraints. Firstly, LIGO, the Laser Interferometer Gravitational Wave Observatory, spends billions of dollars to detect the gravitational waves. I cannot afford to spend this much, and thus money is one problem. Secondly, the arm lengths of LIGO are each 4 kilometers long. That would extend way beyond the school's compound. Hence, space is another problem. These are the two primary constraints to create an interferometer. The Michelson-Morley experiment is constructed by two mirrors, one adjustable mirror and one fixed mirror, as well as a beam splitter to split the light in two, a PCV lens to enlarge the image, a screen to display the image, and a laser. These have to be perfectly set up for a fringe pattern to appear. As light is very sensitive to motions, you need to be careful when adjusting the laser and the mirrors. My first prototype was meant to test out one of the mirrors and investigate the beam splitter. I also wanted to test how each item worked, as I have never used a beam splitter, a PCV lens, or an adjustable mirror. I set up my first prototype with temporary boxes and tapes. From this prototype, I learned to keep both mirrors equidistant from the beam splitter, keep the laser parallel to the ground, and have all the items on the same level. This helped me set up my second prototype. For the second prototype, I drew out all the positions for my equipment. I measured distances precisely and measured angles very accurately. Then I placed the items in the designated places. From this prototype, I figured out I needed a base block for the two mirrors and a laser stand to hold the laser still. I gathered two wooden blocks and a stand for my third prototype. With this, everything was set on the same level. The distances were measured and calculated and all the equipment was set. With slight adjustments using the adjustable mirror, I finally got a fringe pattern showing the constructive and destructive interferences of the light waves. This is the fringe pattern of the interference of light waves in superposition. Superposition is a principle where two or more waves overlap in space and the resultant disturbance is equal to the algebraic sum of the individual disturbances. In this image, you can observe the constructive and destructive interferences of light. The constructive interferences occur when the two light waves are in phase. This is seen where there are red horizontal lines. On the other hand, destructive interference occurs when the light waves are out of phase, resulting in little or no light on the fringe pattern. Although I constructed a Michelson-Morley experiment, a gravitational wave detector operates in a similar fashion. LIGO also has two mirrors, a laser, and a beam splitter to split the light. However, LIGO extends 4 kilometers from the splitter to one of its mirrors. Moreover, LIGO reflects the light 300 times back and forth, resulting in the light traveling 1,200 kilometers in total. The detector at LIGO can also detect a motion that is 10,000 times smaller than an atomic nucleus. This is all to detect a difference in space of 10 to the negative 19 meters, created by a gravitational wave. My biggest success and achievement in the project was being able to construct the interferometer. Other successes are understanding how the superposition of wave occurs, learning about previous LIGO detections, and making some calculations on the actual Michelson-Morley experiment. However, I would have liked to explore more about the mathematics behind the gravitational waves. Although they are very complicated with multivariable calculus, I would have liked to see how the solutions to the general theory of relativity yield the waveform of the gravitational wave. This was my failure, and I would have done differently by diving further into the mathematics. Although I knew my passion for astrophysics and theoretical physics, this confirmed that I really do want to pursue the field of physics for my future. I also learned my interest in the mathematics behind the gravitational waves and the general theory of relativity. This course helped me develop engineering skills in constructing the interferometer, as well as the mathematical skills to analyze the experiment.